So in this section, we are going to talk about accumulation functions and definite integrals in applied contexts. So we had something similar to this back when we were doing derivatives about contextual information. So this starts on page 7 of your notes, and your homework is found on page 8. Your homework is these 3 cons. So our essential question for today is, how does the context of the question relate back to accumulation and definite integrals? In other words, it relates back to the fundamental theorem of calculus part 1. That's really what it's going to relate back to. So really, these are applications using the fundamental theorem of calculus part 1, which you've already used quite a bit in the last unit. We really rely heavily on it. So I think you probably have a good comfort level with that. So again, essential questions right up here. So let's just kind of review the fundamental theorem of calculus part 1. Remember that this fundamental theorem of calculus part 1 represents a change in a value. So in other words, it represents the change in this value. We know a change is a difference in a value. So here's the difference, and this difference is in the antiderivative. It's the difference of the antiderivative value. So the fundamental theorem of calculus represents a change in the antiderivative value. And if we don't have the antiderivative, if instead we have the derivative, that means we can integrate the derivative. So there's 2 ways to get express this and get an answer. We can either integrate the derivative, or if we have the antiderivative, we can find a difference between the 2 values that start at A and end at B. So let me just kind of throw this at you as a little reminder. This isn't in your notes, but let's go back to our anchor chart we did earlier this year. The fundamental theorem of calculus said that these 2 things will yield equal values. So if we look back at this anchor chart we did a while ago, we accumulated the area underneath this linear function, and that linear function was 2x. And so accumulating the area meant we could geometrically determine this region from 2 to 7. And we know that we got 45 for that. And then we looked at the antiderivative, and we noticed that the antiderivative was x squared. So when we look at the antiderivative, if we take the difference of these 2 values, so the value of the antiderivative at 7 is 49, right? Here's 7, and the value of the function is 49. And the value of the antiderivative at 2, here's 2, is 4. So if we take a look at this difference here, we also get 45. So we get 45 if we integrate the derivative, and we get 45 if we take the difference of the antiderivative. So that's the fundamental theorem of calculus, and that was the whole basis of that anchor chart there. Okay, so back to the notes here. We know that the derivative is a rate. So really what we're going to focus on with these questions is making sure that the information that we are given is a rate. So for instance, just to relate this back to motion, we just kind of discussed motion, we could integrate velocity, because velocity is a rate, and that is equal to the change in position, or what we call displacement. Or we could also integrate acceleration, because acceleration is also a rate. It's the rate of change in velocity. So if we integrate the acceleration, then we get the change in velocity, and those 2 things are equal. So those are just some examples from the last class that we had. So in general terms, if we integrate a rate, that should equal the change in the antiderivative. Okay, so integrating the rate equals by how much the value changes, the antiderivative changes. So let's take a look at a variation then, because this is a really common variation, and we've used this too. We would call these initial condition problems. We can then look at the context of the problem to determine which one of the above expressions we're being asked, and adjust the fundamental theorem of calculus part 1 accordingly. So when I say which one of the above expressions, if you're looking at your notes, this is all above, right? So which one of these expressions are we being asked for in the question, in the context of the problem? So what's really common, for instance, is to be asked for a final value. Okay, and so when we look at I'm going to switch back again. When we look at the fundamental theorem of calculus of part 1, as it's typically written, the final value is FB. So we're being asked for the final value, we should be rearranging to solve for f of b. So if we solve for f of b, that means adding f of a to both sides, and we get an expression that looks like this. And we would typically call this variation an initial condition problem or an initial value problem, right? Because this is the initial value. We start at a, we end at b. So this is our initial value because it's the value at a. And then we integrate the function between a and b, so we have an initial value. We add on the change, we get some final value. So this variation is used to answer these type of questions. How much is present at time b or location b? How much do we have? What is the final amount? So asking those type of questions. So let's take a look at these two examples. These are just real quick ones. It says the function b of t gives the number of books sold by a store by time t in days of a given year. Okay, so if we take a look at that, b of t is not a rate. It's the number of books sold. So b of t, if that's not a rate, then if we're going to integrate something, we have to integrate the derivative of this. So integrating this derivative, this is integrating the books per day. If I'm looking at the units here, and we know that b stands for books, and the independent variable t stands for days. So this rate is in books per day. So if we're integrating the rate books per day between 45 and 50, we're integrating the b's rate, right? B prime, that's b's rate. And that's going to be the change in the number of books from day 45 to day 50. So we're going to accumulate underneath the derivative curve, and that represents a change. That's the left-hand side of the fundamental theorem, right? That's finding the area, and that's the change from 45 to 50. Just like in our anchor chart, we have the change from 2 to 7. Here's another example. The cumulative cost of purchasing and maintaining Julia's computer is increasing at a rate of R of t dollars per year. Oh, whoops. Let's finish this off then. So if we were to write this in terms of the fundamental theorem, sorry about that, we would write that this equals b of 50 minus b of 45. These are the antiderivative values. Okay, back to example 2. So we have a cumulative cost. That's some sort of future value. But we have a rate here. And I'm trying to color code. See how I used green for rate here, and I'm using green for rate here. I'm trying to color code here. I'm using red for final value or some future value. I'm using red for future value. So I'm just going to keep that in mind. So increasing at a rate of R of t dollars per year. Couple of things when we're dealing with these contextual problems. They love to use R of t because and most often that R refers to a rate. So that should be kind of an indicator that they're probably talking about a rate. But again, these are contextual problems, so we have to get our clues from what the problem says. So we know that R of t's units is dollars per year. Anytime we see this per, I should really have this underlined, this per year underlined. Anytime we see the per statement, we know we're dealing with a rate. So this is a rate. So it says where t is years. Okay. At t equals 1, Julia has spent a total of $420 in her computer. So t equals 1 after 1 year. In the first year, she spent $420 in her computer. It's probably how much her computer cost. So here's the 420. This 420 represents big R, if that makes sense. Big R of 1, if you think back to the fundamental theorem, plus the integral from 1 to 5 of the rate R of t, little r, dt. So we have the amount that Julia spent in the first year, plus any accumulated costs from years 1 to 5, and that equals 570. So what does that mean then? So we know that this 420 That's the beginning value. That's our initial value. That's our big R of 1. We know this is the rate. It's the change in money. It's how much, from year 1 to year 5, how much Julia spent on repairs or upkeep or anything like that. And so that final amount, that 570, is the total money spent over, including that first year, and so for the beginning cost plus years 1 to 5 for any maintenance or upkeep of her computer. So that, what does that mean then is, what this statement means then is we know that she has spent a total of $570, including buying and maintaining her computer. So that's kind of how we get we use the context of the problem to give the problem a meaning and determine what different components of the problem mean. So this 570 then is the big R of 5. If you're looking at the fundamental theorem of calculus definition. Okay, let's take a look at some other ones where we actually, we could ask you this question and let me kind of point out the ways in which they ask you to do things. So here's an example. Total number of subscribers Zhang Wei has for his video page, so must be like a YouTube video producer, is changing at a rate of 21 minus 2t subscribers per week. So this is the rate at which his subscribers are changing. So it looks like as time goes on, he's tending to lose subscribers because he's subtracting 2t. And it says at time t equals 8 weeks, Zhang Wei has 120 subscribers. So we have some, and then it goes on to say, I'll get back to that in a second, and then it goes on to say how many subscribers does he have by week 20. So the T8 is actually the initial number of subscribers we're looking for the time interval. So that's our R of 8, and I'm using our big R because it's an initial value, so it's an antiderivative value. And then how many subscribers does Zhang Wei have by week 20? So it's asking us to find some future value here. So in fact, we know it's by week 20, so it's asking us to find R of 20. So we have to put these three things together. And since it's asking us to find R of 20, I'm going to skip right to that rewritten version where it says R of 20 equals the integral from 8 to 20. This is your A to B, so to speak, of the rate, little r of t dt, plus R of 8. So that's that alternative way we can write the fundamental theorem of calculus part 1. And then we know that since we have a function here. Now I could just ask you to set up a representation to describe how many subscribers Zhang Wei has at 20 weeks, and this would suffice. This is an expression that says how many subscribers he would have at 20 weeks. Or since we do have a function, I could ask you to literally tell me how many subscribers he has by week 20. And we're going to go through and do that. So sometimes we just ask you to write but do not solve. And in that case, this expression would be all you would have to do. But I'm going to put in the function here. I'm going to integrate 21 minus 2t. And then I'm going to add the 120 because that's what R of 8 is. So this is physically figuring out how many subscribers he has by the 20th week. So the antiderivative here is 21t minus t squared, right? Bump up the power, divide by the new power. So that's 21t divided by 1. That's 2t squared divided by 2. And we get this. And I'm just going to evaluate this because I know I just have to add 120 to it when I get done here. So I'm just going to focus on evaluating this integral. So I'm plugging in 20. We get 21 times 20 minus 20 squared. And then subtract, plug in 8. 21 times 8 minus 8 squared. Now I'm going to take care of each one of these brackets. Notice my use of brackets here. All right, I got the 20 in its own brackets, so I know that I'm multiplying. I've got square brackets here because I know I'm going to have to subtract whatever answer ends up coming out over here. I'm really using a lot of brackets to organize my information here. Okay, so 21 times 20 is 420. 20 squared is 400. Yes, this is a no calculator problem. You should be able to do that in your head. Now for 21 times 20, I think 20 times 20 which is 400, and then the 1 here is plus another 20. That's how I got the 420 without a calculator so quickly. And then I got a minus sign here, and then 21 times 8, I had to go off to the side and do a 21 times 8. 1 times 8 is 8. 2 times 8 is 16, so I had to do a little off to the side there, and that's fine. Minus 8 squared, which is minus 64. So now I'm going to take care of this. 168 minus 64, that's 104. So we know we have 20 minus 104. And didn't I mention that he was losing subscribers each week because of that minus sign, right? So when I do that subtraction, I get a negative 84. So Zhang, we lost 84 subscribers between week 8 and week 20. So over that period. So I know he lost 84 subscribers. I'm going to put a negative 84 right here. So we have 120 and a negative 84, and so he's left with 36 subscribers after 20 weeks. So just to kind of recap, if it asks you to set up but do not solve, you can set up the fundamental theorem of calculus part 1 in this modified form, or you can set it up with the function inserted. That's a setup but do not solve, and you're good to go there. But if it asks you how many subscribers, it's expecting a numeric answer. Okay. And then if we look at example 4, same sort of example. The reason why I'm if we could compare 3 to 4, same type of example. It's going to give you enough information to find the whole answer, but I really wanted to go over integrating a trig function and then reversing that chain rule, right? All in one step, because we really need to practice that. They're going to ask you to do that a lot on this AP exam, for sure. Okay, so let's take a look at this example 4. We got a water level under a bridge, and it's changing at a rate of 40 sine pi 6 over t, centimeters per hour. So let's think about that. We know that sine is a trig function. We know that trig functions oscillate, right? They go up and they go down, and they go up and they go down, and they go up and they go down, right? They oscillate between two values, -1 and +1, if you didn't have anything but the sign. So we know that this water level is going to oscillate underneath this bridge. It's going to get high, then it's going to get low, then it's going to get high, then it's going to get low. Several times, probably several times per day, because this is per hour. So kind of just to give you a little context of what's happening here. Okay, at time t equals 3, the water level is 91 centimeters. Okay, by how much does the water level change during the 4th hour? So when we think about, when we're watching this, we start at time t equals 0. So from 0 to 1 is the 1st hour. From 1 to 2 is the 2nd hour. Does that make sense? From 2 to 3 is the 3rd hour. From 3 to 4 is the 4th hour. So we're integrating from 3 to 4. In other words, if it's asking you for something during the 4th hour, make sure the 4 is the upper bound. Okay, so we know we have a rate here. I coded it green. We have a rate, a little r of t. We have an initial value of 91 centimeters. That's a big R of 3. And we don't care about R of 4, because we're not asking what the water level is after 4 hours. We're asking how much does the water level change in that last hour. So we're being asked, if we think about this, we don't even need that information because we're really just being asked for this. So this is the fundamental theorem of calculus, part 1. In a very traditional writing, right? Big R of 4 minus big R of 3 equals the integral from 3 to 4 of little r, the rate, dt. But we have big R of 3, but we don't even need it. So notice I scribbled that out, right? Scribbled that out because all we're being asked for is by how much does the water level change? And if all we're looking for is the change, then all we're looking for is the value of the integral, which we have to use because we have no idea about big R of 4. We can't use this side of the expression. So we're going to integrate our rate, which is 40 sine pi over 6 t dt. Now, like I said, the idea of showing you this is because we want to be able to do this as efficiently as possible, integrating this. So we know we can bring 40 along for the ride. The antiderivative of sine is negative cosine. Okay, and then whatever's in here just gets stuck right in here. It never changes. And then, but because this is pi over 6t, we have to divide by that derivative, which is pi over 6. Okay, so we've integrated 40 negative cosine pi over 6t divided by pi over 6. So dividing by pi over 6 is the same as multiplying by 6 over pi. So if we multiply by 6, this becomes a negative 240. And then we have divide by pi, cosine pi over 6t from 3 to 4. Okay, so that means you have to stick a 4 here, which means you get 4 pi over 6, which is 2 pi over 3. And then we have to stick a 3 here, which gives us 3 pi over 6, which is pi over 2. Okay, so I'm going to have you, why don't you pause the video and see if you can work through that using a unit circle. Okay, and then come back and check your answer. I do not have the steps here for working through the unit circle, but like I said, pause the video, work through the unit circle, and then come back and the answer will be displayed when you start the video up again. So assuming that you've gone through plugging in the 4 and plugging in the 3 and evaluating that using unit circle, you should have gotten a final answer because plugging all that in would lead to a negative value, and we have a negative value out front. We end up with a positive value. So we have 120 divided by pi. So that's how much the water level changed. And that's approximately, I really should have an approximate sign there, 19.547 centimeters. So the water level went up by 19.547 centimeters. I just want to remind you, that when we're dealing with giving decimal answers, that the AP calculus standard is 3 decimal places, 5, 4, 7, correctly rounded. Okay, you can give more decimal places as long as they're correct. You can give 4, 5, or 6 decimal places, that's fine. But the minimum is 3, and then that last digit has to be correctly rounded. Okay, so how does the context of the question relate back to the fundamental theorem of calculus part 1? The question has you either finding a change in a value, in which case you just need to find the value of that integration, or how much will be present in the future. That's the big F of B. Both are examples of fundamental theorem of calculus part 1. So at this point, you can do the homework. These 3, the first 2 I think are just setting up expressions. So those should go pretty quickly. And then the last one is actually doing integration to get numerical answers.